Hi guys! This is the second part of the three-part lecture on the topic Applied Maximum and Minimum Problems. We will be doing two problems in this video, and to aid us, you can see on your left side of the screen the steps in solving absolute extremum problems and the steps in solving optimization word problems. Now without further ado, let's begin. So our first example is given by a 1,000 square yard rectangular lot along a highway is to be fenced off such that one side of the fence is on the highway. The fencing on the highway costs 80 pesos per yard, and the fencing on the other sides costs 20 pesos per yard. We wish to find the dimensions of the lot that will minimize the total cost of the fencing. Now this type of problem is very common, and it's also very logical in the sense that we see that a lot that is on the highway costs more than those that are not. And that's the reason why there are a lot of shops where it's elongated because they want to minimize the part on the main road. Now, a very wrong way to deal with this type of problem is to say that to minimize cost means to minimize perimeter, or to say minimize the area. For us to be able to solve this properly, we will be following still the steps in solving optimization problems as is indicated on the left side. Now this is clearly an optimization problem because of the word minimize, and what we want to minimize here is the total cost. Now the figure is already given on the right hand side, and that is, if we have a rectangular lot, then we will be calling S1 to be the length of the side adjacent to the highway, and S2 to be the side outside that is not adjacent to the highway. Also, we will be letting C to be the total cost of the fencing, and because it will be the one that we need to minimize. Now, the question is, how do we obtain the cost of the fencing? Now, each part of the fence, as I point here, has a cost, and the cost per part of the fence is just given by the length times the price. For example, since this is not part adjacent the highway, so the total cost of this length here will just be the length, which is just S1, times the price, which is 20 per yard, and that will give me a total pesos for the whole fence. Since I have 4, I'll just add it. So this will become a 20S2 plus 20S1 plus 20S2 plus 80S1, since the price for this red line here, line segment, is 80 pesos per yard. So I have a 20S2 plus 20S2, that's a 40S2. And then 80S1 plus 20S1 will give me a total of 100S1 plus 40S2. Clearly, this is not in terms of a single variable. So as in step number 4, we need to find a way to reduce this into a single variable quantity. To do that, I will be looking at one of the important given in this problem, which is the area of the rectangular lot. It is already given that the area, whatever the size may be of the length of the side, it should always be 1,000. So this is a constant quantity. And since the area of a rectangular lot is just an S1 times S2, or the length times the width, then I can solve for S2, and that will give me a 1,000 over S1. By substituting this quantity to our minimization problem, I will have 100 S1 plus 40,000 over S1. This is already a single variable quantity, and I will call this function C of S1. We are now done with number 4, so it's a matter of finding the domain. Now, unlike the first two problems that we had in the last video, to get the interval here is not that simple. It's still easy to see that the S1 being a length means that it should be positive, and thus our constraint should mean that S1 is an element of 0 to something. The problem is we do not have a limit to that number, primarily because if I make S1 bigger, there is no limiting quantity there. As you may see, if I make S1 bigger, it can just become big and big and big. And the only constant one part here is 1,000. So what will happen is that when S1 becomes big, S2 will now become small. And since we can do this over and over, there is no definite way to do it in this type of mindset. So what I will be doing is the other way around. Since I know that to make if S1 becomes big, S2 becomes small, I just ask myself, what will happen when S2 becomes small? If I will go back to the right hand side of the slide, you will see here, instead of solving for S2, I solve for S1. The reason why I do that is because if I look at S2 here and I make it smaller and smaller, being a positive number, I will let the limit of this approach 0 from the right. Then 1,000 over 0 from the right will tend to a positive infinity. So that will tell you that the S1 will actually behave going to positive infinity and it will be okay. Of course, in real life situations, you do not let S1 go to infinity because we have a limited length of the road. But at least in this problem, we will be letting it so. Since we now have a function and have an interval, we can now try to use our techniques of solving absolute extremum to solve this type of problem. Since I is not a closed and bounded interval, I will still be hoping for the single relative extreme case. So to find critical numbers, I will get the derivative of this function, c of S1. That will just be 100 minus 40,000 over S1 squared. I will solve for this and I will simplify this. Remember, to get the critical number, I will need to add this and find out the factors of our numerator. You will see here that the factors of this quantity will just be 100 times S1 squared minus 400 over S1 squared. And that will give you 20 and negative 20 that makes it 0 and 0 that will make it undefined. Since 0 is not in the original domain of my function c of S1, then that will leave me with 20 and negative 20. As I have told you in the previous video, this is already a bad flag. Remember, you want to have a single relative extreme case. It's a good thing that if you look at our interval 0 to positive infinity, it is only positive 20 that will be in the interval. And again, emphasizing that it is important to remove the critical numbers of our function not in our interval. This already gives us a good feeling because since you only have a single critical number, there is a high chance that this is the number that we are looking for. But we still need to test since we need to know that and we need to verify that truly C has a relative minimum at 20 so that it becomes an absolute minimum as is indicated in our problem. To do that, I will still be using second derivative test. I will differentiate this again and I'll have a 2 times 40,000 over S1 cubed. Notice, I did not simplify it anymore because the only thing that we really need is the sign when you evaluate 20 on this function, which is clearly a positive number. By the second derivative test, it will tell us that we have a relative minimum, and since it is the only relative extrema, it will also become the absolute minimum. And it is left to show that we need to find also S2. Now, whenever you have a problem of this form, a very important tip that I can give you is that 20 is S1 and that means it is easily obtained. If you want to get the other variable, you need not look at the functions that you see on the board, but rather you look at the original relationship of S1 and S2, and that is their product is 1,000. If S1 is equal to 20, then 1000 over S1, or in this case 20, will give me an S2 of 50. And that will give you the dimensions. Now let's have another example. I want to determine the dimensions of the right circular cylinder of radius volume that can be inscribed in a right circular cone of radius 6 and height 9. This question is a little bit tricky because you will have two figures here. One is a right circular cylinder and another a right circular cone. You can orient them in any way, but I will be orienting it like so. So I am inscribing this right circular cylinder inside, so it will somewhat look like this. So the bottom two corners of the cylinder should be touching our cone, and to maximize the quantity that the volume of my cylinder, this will become flat, as is the top part of our cone. Now this is clearly the cross-section of this quantity. And an important thing to remember here is what is moving and what is not. Remember that the circular cone is a constant figure, and that is, it will always have a radius of 6 inches and a height of 9 inches. It is the circular cylinder that changes. And if you ask why does it change, I mean, I can make the radius bigger, and if I make the radius bigger, it will mean that if I bring this down here, the height will now become shorter. And if I want a longer height, then the radius will be the one to compensate. So there is some sort of compensation truly that is happening between the radius and the height of the cylinder. Now I need the dimensions. So by the second step in our solving optimization problems, I will assign proper variables. Clearly, I can let R to be the radius, H to be the height, and I will be letting V to be the volume that I wish to maximize. The formula for the volume is easy. I need to maximize pi r squared h, which is very unfortunate that it has two variables. So again, I need to find a way to relate r and h. Now, if we only have a right circular cylinder, there is no way to relate r and h. But since we are inscribing it in a right circular cone, there is a way to relate them. Unfortunately, the way to relate them requires insight, which we will be showing in this video. And that is knowing that if we look at the cross-section of the cone and the cylinder as is given by the figure that we have, I can construct two triangles. The first triangle is this triangle here, red triangle. This has base 6 and height 9. And another triangle, which is this blue triangle here. You will notice that they are similar. The blue triangle will have base 6 minus r, and it will have height h. This is thus we will have this equation that relates r and h. Now the next question is, do I solve for h or do I solve for r? If you think that it doesn't matter, then I will of course beg to differ. Clearly, because if I solve for r, then if I substitute that quantity here, I will be forced to square it. On the other hand, if I solve for h, then that means I don't need to square it, and you just need to multiply it here, which of course makes it much easier. And true enough, if I multiply both sides by h in our equation here, I will obtain v of r to be pi r squared times 9 minus 3 over 2r. We now have a function of a single variable. It's a matter of finding the domain. Now this is different from the last example that we have, and that is, it is easy to see in the diagram what are the values of r that we have. This is the reason why it's very important that you know that you have the variable first before the interval. Because clearly, since r is a radius here, it should be greater than 0. And since you wish to inscribe it in the cone, it cannot exceed 6. So therefore, the constraint here will just be from 0 to 6. I now have a function and I have an interval. It's a matter of finding the absolute extrema. This is still not a closed and bounded interval, so I'm still hoping for the single relative extrema case. We get the derivative. Since I have already simplified my function v of r, I will differentiate to obtain this quantity here. This will have two zeros, namely 0 and 4. But I will not be using 0 clearly because 0 is not part of our constraint. And that will leave me with a single critical number of 4 in the interval, which, as I've told you many times, a very good indicator that you are doing it correctly. Now, since I have a critical number of 4, I just need to test whether it is a maximum or a minimum. Hopefully, it will become a maximum. The second derivative will be this, and if I substitute 4 here, I'll have an 18 pi minus 36 pi. That's a negative number, negative 18 pi. And a negative quantity here will mean that we have a relative maximum. And since it's the only relative maximum, it's also an absolute maximum. Now it is left to find the other dimension. I already know the r, which is 4. So I need to find the h. And if I want to find the h, as I've told you before, you go back to the original relationship of r and h. And that is this. If r is equal to 4, I have a 6 minus 4, that's a 2. Solving for h, I will obtain the number 3. Now, in the next video, we will be dealing with our last two examples. So I hope to see you there.